Welcome to the 18th lecture of graph theory. In this class, we will continue with the proof of Kuratowsky's theorem. The theorem says the following assertions are equivalent for graph G. G is planar. G contains neither K5 nor K33 as a topological minor. G contains neither K33 or K5 as a minor. In other words, if G is a planar graph, it is clear that you cannot have K33 or K5 as a minor in it. Definitely, it cannot have K33 or K5 as a topological minor in it. This is obvious because because a planar graph cannot have non-planar minors or topological minors in it. K5 and K33 are really definitely non-planar. Now, the more difficult part to prove is that if a graph does not have a K5 or K33 minor, then it is a planar graph. In other words, any non-planar graph should have one of these minors, either K5 or K33 minors. As we have seen in the last class, it is equivalent to saying that any non-planar graph will have either a topological minor of K33 or K5, because if we have a K33 or K5 minor, then definitely we have the corresponding topological, some of the either a K33 or K5 topological minor also. So, if K33 comes as a minor, then K33 will be there as a topological minor also. On the other hand, if K5 comes as a minor, you may get either a K5 topological minor or K33 topological minor. So, therefore, it is enough to show that any graph without a K5 or K33 topological minor will be non-planar, will be planar. But we will prove it for 3 connected graphs first. That means, if G is a 3 connected graph and it does not contain K5 or K33 as a minor in it, then it is planar. This is what we will prove. Then we can extend it to 2 connected or even other cases, the connectivity less than 3 cases. It will be easier to do. Now, how do we do this thing? So, this is the theorem we want to prove. Let G be a 3 connected graph and it does not have K5 or K33 as a minor, then we want to show that it is planar. So, we will just show a planar drawing of it. This is our plan. So, we will use induction. Let us say that for all graphs with smaller number of vertices, it is true. So, with number of vertices K4 or so 4 or less, it is very trivial, because if K4, of course, it is the first 3 connected graph we can start with, and K5 or K33 minor is not there in K4. Now, it is a planar graph, it has a planar drawing, therefore, it is true. Now, by induction, let us assume that for smaller number of vertices, the statement is true, and now we need to consider graphs with n vertices, say number of vertices n, and 3 connected and without K5 or K33 minor. Now, the point is, because it is a 3 connected graph, there is one edge in the graph such that if you contract that edge, the resulting graph is still 3 connected. This theorem we had studied in the when we studied connectivity. So, this is a theorem by Thomason, and we can use this theorem here. How do we use it? So, we pick up this edge. We know that such an edge exists. So, xy, let us say xy, and so such an edge, if I identify and then contract that edge, right. So, this such an edge is there x y. The point is if you contract it, so we will get a new graph. So, with that contracted edge will be v x y. You know, after contracting what will happen is, so the neighbors of x and y together will be the neighbors of v x y, right, the neighbors of x and y. Now, we can definitely be, this is a smaller number of vertices here, the number of vertices is smaller here and it is 3 connected, and of course k 5 or k 3 minor cannot appear after contraction, because after contraction the resulting graph has, if the resulting graph has k 5 or k 3 minor, then the original also will have obviously. So, because contraction is one of the operations defining the minors, right. So, therefore, we can see that this resulting graph also does not have k 5 or k 3 minor. So, induction can be applied on that. By induction assumption we know that it has a planar drawing, and in particular the drawing somewhere this v x y will come, right, v x y will come, and you see suppose see the v x y, some the edges on v x y will go out of it, and where will it go. So, the point is, suppose if I had removed this vertex v x y from the graph, it is because we have a 3 connected graph here, after removal of v x y we still will have a 2 connected graph, and so this, so in a 2 connected graph the any plane drawing, the each face has its boundary as a cycle, right. So, a simple cycle will come. So, it's so therefore, we know that the face in which this particular point is contained, that also will be, suppose this is the face of that. So, that will also be a cycle, you know. So, if you remove this vertex v I, suppose I'll remove this vertex v I. So, this is what we will see v x y, this is what I will see, right. So, now you see that these edges were going somehow to these some points on the boundaries, right, that is the only way it can go v x y. So, now suppose I had removed, so v x y remove, remember v x y was formed by contracting x and y. So, essentially these neighbors some of them are from x, some of them are from y. So, see they might have come mixed up, but let us say first we consider the neighbors of x alone, right. So, that means some neighbors may disappear, maybe suppose this disappears, right. So, we only retain the neighbors of x, right. Suppose these are the neighbors of x. So, I can draw like this. Yeah, I can draw like this. So, this is now instead the point where v x I will just put x, and then some of the neighbors, the neighbors of x which were not neighbors of y are drawn, right. Now, the point is look at the y neighbors, the neighbors of y, sorry, neighbors of x, all the neighbors of x are drawn. Now, I can look at the neighbors of y. How can they come? So, suppose, so there is a region here. So, this essentially we have several regions on the boundary of this face. So, which is essentially given by the positions of the neighbors of x, right, one region, another region, right, another region, right, another region, another region. So, is it possible that we have some y here inside? Suppose is it possible that you examine each of these regions other than say not touching, not including the neighbors of x itself? Is it possible that no y appears in the interior regions anywhere? So, that means the y's are always on the positions where x neighbors are placed, right, the same vertices, right. That means essentially y will share the neighbors of x, but then at least 3 neighbors should be there, y should have at least 3 neighbors, right. So, y should have at least 3 neighbors. So, so it will so happen that, so we can right. So, it y can be like this. So, it can be some 3 neighbors, it can be. Okay. Now, what do we see if y has 3 neighbors, shared neighbors with x. So, see, need not be this consecutive, you can x can have other neighbors also here. So, suppose this neighbor of x, this neighbor of x, and this neighbor of x is shared by y, right, and see y x also has so then you can see that the 3 neighbors together will form. So, these 3 neighbors together will form 1. So, say I can draw with black. So, this 1, 2. So, because these are the 3 neighbors which x shares. So, 1, 2, 3. This is a triangle here, that these 3 neighbors, and then this is connected to this, and x is also connected to this, and this, and between x we have. So, essentially we have a connection. So, essentially we have a K5 available here, right. So, more neatly we can draw here. So, it will be so this is the x 3 neighbors. Now, between them, so we see the triangle. So, 1, 2, 3. Then the y may be here, y, and y is also having these 3 neighbors. So, together we have a K5 here. So, this triangle, this, and this together we have a K5 minor here. So, it is a contradiction to the assumption that there is no K5 minor in the graph. So, see, of course, you can assume that when I selected between x and y, so I decided that x has smaller neighbors than y. So, suppose y has only 2 neighbors, right. So, y has only 2 neighbors. So, then it will so happen that x also will have 2 neighbors maximum, and these 2 neighbors. So, if I remove these two neighbors, right, see, because x should have, so this is x, y, at least 3 edges should be going out of x and y. So, because they are 3 connected. So, if there are only 2 neighbors for x, then y also, then x also has only 2 neighbors, and then together this removal of these 2 vertices will disconnect this portion from the rest of the graph. So, therefore, it will not be 3 connected, right. So, that is why we are saying that there should be at least 3 neighbors of y, and if they all are shared with x, then we already got a K5 minor, right. Now, it means that there should be some, let us again draw this thing x in this interior region of this thing which we have marked here, this region, and this region, which is not including the neighbors themselves, the position of the neighbors themselves. There should be at least one neighbor. Let us say this here, at least the y has, so I am drawing y here. So, y has at least one neighbor here, right. Now, where else can y's neighbor be? So, I am claiming that all the neighbors of y has to be in this region then. in the same region, in the same segment here, right. So, y suppose including this, we can have I can share these neighbors of x, but it cannot go beyond this thing. Suppose it goes beyond this thing, suppose say y has a neighbor here, right, here or somewhere else. So, then what happens is, so you see this connection is there, so these two are there. Now, you can see that here we have already got a K4 K22, right, K22 including this vertex and this vertex and this vertex already defines a K22 like this, minor K22 minor here, right. And then now here is the third, we can make a K33 by adding this and this on different sides of the K22, right, because this on the A side, this on the B side, right, and this two neighbors can be on the A side and these two neighbors on the B side, right. So, this will make a this three vertices, and then this and this will be the other three vertices. So, this will be x, this will be y, and these are the two neighbors of x and these are the two neighbors of y. We have this connection, right, and we have this also here, because that is what the circle provides that connection. So, here to here on edge, here to here on edge, here to here on edge, and here to here another edge K4, sorry K22, right, that K22, and together with this thing will give you a K33 minor, right. So, this tells us that so maybe we can draw it a little more clearly. So, I am showing you the K33 minor in case, so this is x neighbors, this is x neighbors here, suppose in between here, so y has a neighbor, and then suppose y has a neighbor beyond, not in this region, I suppose beyond this region. Then what happens is y, I take y, so this sorry, okay, I can color it yellow as these two, and this is y, okay. So, these three as one side, and then x, sorry, this I'll use orange color, yellow, this and this on the other side, and here we have the connections. So, here is a connection, sorry, here is a connection, here is the 3 connection to the yellow vertex, and then this yellow thing, there is a connection, there is a connection like this here, and there is a connection here, and then there is a connection here. See, this is, so there is every vertex is connected to every brown vertex is connected now to every brown vertex is connected now to every yellow vertex. Every brown vertex is connected now to every yellow vertex, and every yellow vertex is connected to, this is a K33. It's a K33, right. So, what we infer now is that all the neighbors of, suppose this is the thing. So, if you consider x, and this is the position of x, and all the neighbors of y should be in this region only. So, x may have some other things here. So, all the neighbors including these points, so y's neighbors all will come here. So, which means that I can place y somewhere here, and then I can if necessary I can connect them like this, and then so this will be a planar drawing of the original graph. See, the key point is we can argue out that y comes in one of these sectors, right. So, inside, so it will not there won't be any confusion about how we can place y with respect to the graph which contains only x after removal of y, right. We can nicely place it in one of the segments, and all the neighbors of y will be inside this region only. So, that is why we can get a drawing of the graph from the smaller drawing. So, it follows that, so if there are two things we have made use of. One is there is no K33 minor in the graph, then one is K5, the graph is K5 minor free, another is the 3 connectivity. If all these conditions were met, then we have argued that we can get a planar drawing of the graph, that means the graph is planar, right. So, we using induction. So, now the only thing left is to show that suppose it is not 3 connected. So, the connectivity is only 2 or 1 or something like that, then also we can get a planar drawing provided K5 or K33 minor is not there. So, what we can do is, suppose the connectivity is 2. So, that means there are 2 vertices, right. So, when you remove these 2 vertices, they will get disconnected into 2 pieces. So, we can see that. So, there are 2 possibilities. So, then here there is an edge or there is no edge. So, whatever it is, we can assume that there is this edge. We will, if it is not there, we will put it, right, and then we consider this graph. This is G1 and then this is G2. You see, by putting this edge, it's easy to see that K5 or K33 minor will not be introduced if it was not there before. We leave it to the reader to verify that. So, the why is it so? Because again, suppose the minor is intuitively, this is the reason, suppose the minor, such a minor is introduced. So, you can see that this edge, right, because it is a 2 connected graph, even if the edge is not there, right, the minor which got introduced here has to be totally from G1 or totally from G2. It is not possible that the minor shares its branch vertices from G1 and G2. So, a little bit of it is here and little bit of here. So, because it has to be totally from here, because this K33 and K5 are the 3 connected graphs. So, for instance, if there is a branch vertex here, so how can suppose how can they share it between the 2 sides. So, suppose if there is one vertex here, right, and so all the other branch vertices are on this side, right. So, it has to have paths to the other side. If there are 3 vertices on this side, there should be 3 different paths from here to here, right, because of the 3 connectivity, and that is not possible because there is only 2 vertices in the separator. We can only have 2 disjoint paths. So, we can infer that if K33 or K5 is a minor of this entire graph after putting this edge, right, then it is completely from this part or completely from this part. We can see a K5 or K33 whichever is in G1 or G2, right. And now, even if this edge was not there, we could have contracted, suppose it was there, K33 minor came in this thing. So, we say that okay, that this edge was critical for that, but then this edge can be produced by contracting this entire portion, because there is at least 2 edges here and there should be, because of the connectivity of this, there should be some path, and then this will become an edge here, right, when you contract this entire region into here, right. So, so therefore, it will so happen that, so we can produce this K33 minor in the total graph also, right. So, in other words, if you consider the connectivity as 2, or for that matter even 1, even in this case it is like that, the argument is correct, right. So, the assumption that the entire graph does not contain K33 or K5 as a minor in it means that so this portion alone or this portion alone also does not contain K33, also K5 minor. Similarly, if it was the connectivity was 2, if this was the picture, then this portion or this portion, even with an addition of this edge, cannot contain K33 or K5 as a minor, because if that minor is there in one of them, it should have existed in the bigger graph also, that is the reason. So, then we can see that the smaller portions can be drawn because they are 3 connected and or by induction we can say. So, the smaller pieces can be drawn on the plane, and then we have to do some scaling and adjusting. So, what we do is we can draw one of them and identify the edge and make sure that that face is right, consider the face in which that edge is appearing, and then we have to make the other part smaller and bring that edge on the outer face and then draw it. So, I will leave it to the student to verify this details, but it is not very difficult. So, or other rigorous treatment is available in Diestel's book. So, you can read from there. We will skip that portion to avoid tedious details. So, the point is just to imagine 2 plane drawings for G1 and G2 and think how we can draw a plane drawing for the complete graph by pasting them together on the correct place, because there is a edge, one edge, and that and not that the face containing that edge can be made the outer face, and we can bring that particular edge in the correct position after making it smaller, the picture making it smaller, and then we can paste it in the correct place and get a planar drawing. That I will leave it to the student to figure out the technical details of that. So, the more interesting portion was to prove it for 3 connected case, right. So, now with this thing we will finish the planar portion. We will revisit planarity a little later, but today my intention is to do a different kind of coloring, a different kind of coloring called list coloring. This is also an important topic in the. So, this is the way we are defining the list coloring. So, we are given a graph, and along with the graph, for each vertices of each vertex of the graph, we are given a set of colors also. That means essentially to each vertex we are associating a list. Our condition is that the vertex should be colored from using one of the colors from that list, or in other words the vertex does not allow any other color, any outside color. So, it has a list of colors, and it is insisting that it will get colored by only one of the colors from that list. So, a coloring such that each vertex gets a color from the list associated with it is called a coloring of the graph from the list. Then we will say that a graph G is k list colorable or k choosable if for every family. So, SV, so with the cardinality of the list equal to k, then there is a proper vertex coloring of G from the list. See, the point here is the list can be anything, but the only thing we know is each vertex has a list and it has at least k colors in it. The content of the list may be anything, but just the length of the list or how many colors are there in the list is known, k. So, but then we should be able to say that irrespective of whatever is in the list, as long as the list sizes, the cardinality of the list are at least k, we can come up with a coloring for each vertex such that the color is from the list for each vertex, and it is a proper coloring, In that case, we say that the graph is k list colorable. See, suppose if a graph is k list colorable, then you can So, okay, fine. And another thing we need to understand is, so suppose this k, the smallest value of k for which this happens is the smallest value of k for which this happens is the least coloring number, least chromatic number of the graph or choice number of the graph. So, we also say that the graph is k choosable. So, the smallest k for which the graph G is k choosable is the least chromatic number of the graph, least chromatic number of the graph. The now the, so of course, to understand it, for instance, you may see you may say, why, for instance, can I suppose can I color a graph, suppose every vertex has the same list, same vertices, the list of size 1, then definitely you cannot color it, because then the each vertex says that I have to get this color only, right, for instance. So, if there is an edge. So, but on the other hand, so if a graph is k list colorable, if a graph is k list colorable, that means irrespective of the list, content of the list, just the guarantee that each list has at least k colors in it tells us that the graph can be colored with the colors from that list. Then it is also clear that it is a k colorable, the usual sense of the coloring. Why is it so? Because we can associate with each vertex the same list, namely 1, 2, 3 up to k, and that means that any vertex can be colored with any of the colors from 1 to k, right. So, in that case, if a coloring happens, that means it is a k coloring only, because we say that k, we can get a coloring of the graph using k colors, right. So, because we are not restricting the colors that can be assignable to a vertex, other than saying that it has to be from 1 to k, right. So, therefore, it is very clear that the choice number of the graph G is always greater than or equal to chi of G, right, because if the choice number is some k, then chi of G also, chi of G has to be k or less, right. So, but sometimes choice number can be much greater than chi of G. So, the next our see the, and another thing is, for instance, you can see some of our earlier bounds, like the greedy coloring strategy. Will it work in the case of list coloring also? So, you can see that suppose you have an ordering of the vertices in such a way that, so I write the vertices in the order V1, V2, V3, V4, Vn, with the property that Vi, right, has at most k neighbors in, say, V1, V2 up to Vi minus 1. Suppose such an ordering, says we have seen that in this case k plus 1 colors are enough to vertex color the graph. Why? Because we will color V1 first, and then V2 first, V2 second, and V3 next, and so on. Whenever I try to color Vi, the vertices starting from V1 and ending at Vi minus 1 has got colors, and when we look from Vi, we see that only at most k neighbors of it are colored. Then we can use the k plus 1th available color for Vi, and therefore it can be colored using k plus 1 colors. This was the greedy strategy, and then essentially we told k plus 1 as the coloring number, right. So, or k was the degeneracy of the graph. Now the same k can be an upper bound for the size of the list, so that we can come up with a coloring of the graph, right. Or in other words, the choice number or the least chromatic number also can be upper bound by the same k. How is it so? Because now to each vertex we are associating a list of cardinality, at least, sorry, this k means k plus 1, I mean the list, a list of size k plus 1 or more. And now when I color starting from V1 and then V2 and V3 and onwards, when I reach Vi, we see that we see that the colors which are already used on its neighbors, right. See, essentially because Vi will see its colored, all its colored neighbors are from in the range V1, V2, V3 up to Vi minus 1, and then we know that only k neighbors are there, only k colors are used up, but its list has at least k plus 1 colors. There should be one more color available to it in its list. So, it has to take from its own list. Earlier we were using just any available color, now we have to insist that it has to use a color from its own list. So, but then because any list has at least k plus 1 members, then you can always get one more color, and therefore it is possible. So, the same argument works here also. Therefore, degeneracy plus 1 of the coloring number is still a bound for in particular maximum degree plus 1 is a bound, right. Similarly, Brock's theorem can be proved also for this case without much effort. So, therefore, we see that some of the bounds which are working for the vertex chromatic number is also an upper bound for the least chromatic number. Now, the next point is we have to see a case where the for instance planar graphs, if you consider, it is 4 colorable vertex coloring, but then it needs 5 colors for least coloring, right. So, its least chromatic number is 5, but how do we show that the planar graphs are 5 least colorable? How can I show that if with every vertex if I associate a list of cardinality at least 5, then we can always come up with a proper vertex coloring of the given planar graph from the given list, right. So, to do this thing, so this is our next team. So, this also a result from the Mason. So, we will show that this every planar graph is 5 choosable. So, the key point here is to rather than, see, this is an induction proof, but rather than doing the induction directly on the for this statement, like means every planar graph is so let us consider a smaller planar graph and assume that it is 5 choosable, then I will try to extend the 5 least coloring of this planar graphs to a bigger planar graph. This is not the strategy. Rather than doing this thing, we will slightly strengthen the induction assumption, and then we will prove the induction for that stronger statement. This is a slightly delicate strengthening of the induction hypothesis. This is the trick here. So, how are we going to do this? So, this is the strengthening. So, now suppose that every inner face of G is bounded by a triangle and its outer face by a cycle. So, we consider a plane graph, plane drawing, and we say that suppose there are several inner faces, all of the inner faces are just triangles, and outer face is bounded by a cycle. So, V1, V2, V3 up to Vk and V1. So, it may be a k length cycle. Suppose further that V1 has already been colored with color 1 and V2 has been colored with color 2. Suppose finally that with every other vertex of C, a list of at least 3 colors is associated, and with every vertex of G minus C, a list of at least 5 colors is associated. Then the coloring of V1 and V2 can be extended to a coloring of G from the given list. This is what we are going to prove. So, in other words, so you consider a special planar drawing. So, the requirement is that our outer face is the only non-triangular face which we are allowing. All other interior faces should be triangles, already triangles. So, and so this can be numbered, say V1, V2, V3, V4, V5, V6 and so on to Vk. This can be numbered like this. The inner faces are triangles, the outer face only is a k-length cycle, and now also we assume that this is colored, this is also colored. These two colors are already known to us, right. Now we will say that the lists are there for suppose a vertex like this. For a vertex like this, there are 5 colors associated in the 5 lists. The lists are of cardinality 5, each list contains 5 colors in it, but the vertices on the face, they contain only say 3, there are only 3 colors in it, they can be any 3. So, only 3 colors, right. So, see, it is possible that this red and green also may be part of that. This V1 and V2 are already colored, those may be part of these things, but we do not have any control on it, but at least 3 colors are there, right. Now, we say that, see, we can get a coloring of this planar graph, see this kind of a planar graph from the lists, each vertex will get the color from their own list, and we can retain in that coloring, we can even retain the already given colors of V1 and V2. This is what the strengthening. Suppose this is true, this statement is true, this is a stronger statement than what we need. Why is it so? You may say that why it looks like a special planar graph. It is not the case, because you see if you are given a planar graph, you can always add edges to it, and because when you add more edges, the requirement of colors may only go up, right. So, if after adding a few more edges, if you can still color that graph, then the earlier graph can definitely be colored, because after removing the edge, the coloring will not be spoiled. So, the more edges only create trouble. So, what we do is we make the planar graph maximal by adding as many edges as possible. So, when the planar graph becomes edge maximal, that means it is a triangulated planar graph, the outer face will become a triangle. So, we can say that here, right. So, already 5 colors are there, suppose 5 colors are given to all of them. Now, let us color this V1 and V2 with 2 colors, say red and green, and then you see red and green, and then here of course, this is all the conditions of this thing, this is a triangulated graph, and then all the conditions of that statement is met. This outer face, this is already colored with one thing, and this is 5 colors instead of 3. In fact, all the interior faces have 5 colors, and therefore, interior vertices have 5 colors, and interior faces are all triangles, and here the exterior face, outer face is also a triangle, that is all. So, therefore, definitely if that statement is true, you can extend this coloring V1 and V2 has already got colors, and everything can get a color from their corresponding lists. So, therefore, if this statement is proved, then whatever statement we are looking for, that means the planar graphs of 5 choiceable is immediate, because we just have to consider the maximal planar graph, that is because the outer cycle becomes a triangle in that case, that is all. And now we see, so therefore, we just have to prove this thing. So, essentially we are trying to prove a stronger statement, therefore, right. So, because here we have much more things, because you know that some of the vertices have only 3 colors in it in their list. So, the remaining things have 5 colors, but 2 vertices are even pre-colored, I mean in the sense that they already got their coloring. Therefore, it will require some more effort. We will assume that it may require some more effort, but it so happens that this strengthening helps us to prove it faster, because the induction hypothesis also gets strengthened, right. Now, let us say this is the thing. So, we will consider this outer cycle. So, the outer cycle is like this. So, this outer cycle. So, this is V1, V2, V3, V4, V5, V6 and Vk, right. So, first thing we do is we see whether there is any chord for this thing. Is it possible to find some chord? Say this is a chord, right. This is a chord, means some vertex to direct edge connecting some Vi to Vj, some Vi to Vj. This can be. So, is it possible to find such an edge, right. So, see, it is not necessary that such a chord exists. Suppose such a chord exists, that means it is a direct connection from some of this. Direct connection means non-adjacent vertices on the cycle are connected by a chord. If such a chord exists, then what happens is you can see that here there are 2 cycles visible, right, one, and this definitely is a smaller the number of vertices in this induced subgraph will be smaller, right, here whatever. So, and of course, this will be triangulated inside, right. So, whatever. So, therefore, all the conditions required for that statement is met, because each interior face here is triangulated, and here all these things have 3 colors associated with that. You can give some color to this thing, whichever from their list, one of the colors, without, because there are 3 colors, one color here and then another color taken from this thing, and we can get a coloring of this thing by induction hypothesis. Now, once you color this thing, so we can consider this portion. So, this portion means here see these 2 vertices have already got colors because of this coloring of the other part, and nothing is shared other than these 2 vertices, right. These 2 vertices are colored. Now, all the other conditions like interior faces are triangles and all are true here also, right. So, and here if you go through they also have 3 colors in their list. Interior vertices will have 5 colors. The only thing is that these 2 has already got colors from the coloring of this part, right, this brown part. So, therefore, we can apply induction on this thing and this portion and get it. See, therefore, if there is a chord for the outer cycle, then we are easily through. The reason is that chord will help us to see this outer cycle splitting into 2 different cycles, one this here and the other this here, right. And for one of these induced subgraphs here, this cycle and the interior vertices thereof, we can apply the induction and get the coloring as we need, and then retain the colors for these 2 only common vertices, and then extend the coloring to the remaining part, the green cycle here, right, and the interior vertices. So, that case is easy. So, if there is a chord, then the things becomes easier in this case. So, therefore, what we are going to do now is to assume that there is no chord. That means, so this is this is our cycle, the outer cycle. This is say V1, V2, V3. So, this is our Vk. So, Vk minus 1 and so on, right. There is no chord. That means nothing like you cannot see any chord here. So, in particular, if I look at this Vk and Vk minus 1, and if you look at the shortest path from Vk minus 1 to V1, it will contain more vertices, right, 1 or more vertices in it. It won't be a chord, direct won't be there. Now, you see that if it is a shortest path, right, and if you look at the neighbors of, so this, okay, there is a path here. If you look at the neighbors of Vk, so Vk minus 1 is one neighbor, so we get some neighbors here, right? It will look like this, and then you can see that. So the, because of this, because inner faces are triangles, so it should, right, so essentially there should be a edge here. So now this, along this we should get a path like this, right? The neighbors should, along the neighbors we should get a path. Okay, along the neighbors we should get a path. It's not even possible that there is some gap here, because once again if you look at this thing, it's not possible to have a vertex of this sort also, otherwise, because how can it be a triangulated face, right? It's not possible. So it should be just including these neighbors, we should have a path from Vk minus 1 to V1 along with this stuff, because that is the all, because all the inner faces are triangulated. This face has to be a triangle, and this face has to be a triangle, then the next has to be a triangle, and the next has to be a triangle, and then finally it has to reach here. So this is the picture we get. Now what we do is, so here see, recall that by our assumption we have V1 and V2 have colors. So this is colored 1 and 2, suppose. So maybe you can use 2 colors for this thing. Say this is already pre-colored, let's say this, maybe its yellow color is already there, violet color is already there, violet color is already there. So now yeah, so now V1 and V2 are already colored. So now what we do is, so here we will look at the list of colors of this. There are 3 colors on that, right? 3 colors. So now 3 color, out of these 3 colors, one of them can be this color, sorry, this yellow, but then there are other 2 colors other than yellow, right? So those 2 colors I will remove from each of these neighbors, except here. Here I will retain like this, because here this has only 3 colors, Vk minus 1 only 3 colors, we cannot get rid of 2 colors from that, because the number of colors will go down. So the Vk we will not disturb, but all these case internal vertices, they had 5 colors in them, therefore we can get rid of 2 colors from that. Which are the 2 colors? Because Vk had 3 colors in it, so other than the yellow color which is already on the V1, we will take out the remaining 2 colors and then get rid of all those things from here, right? Now what happens is, when my plan is to consider this this cycle, so this entire cycle, so this is the root excluding Vk, right? So now you see that all this V1 and V2 has already got colors, V3, V4, all these things up to Vk minus n had 3 colors, we haven't disturbed them, and then these guys which had before 5 colors have lost 2 colors from them at most. Maybe it might not have lost, but then if they had shared some colors with Vk, they have lost those 2 colors from them, right? Now let us say those 2 colors which were removed were red and say green, red and green color were removed from the list. So they also have, because initially they had 5 colors, now 3 colors are this thing. Now you know that by induction this can be colored, because all these are interior faces are triangles, and all such assumptions are still true here for this thing, and these 2 are 3 colored, and every outer face has 3 colors and every interior face has 5 colors. Therefore it can be, because the number of vertices is reduced by 1, it can be colored from the list, right? Now what we do is, you look at the color, by that coloring which color came for Vk minus 1. See, if it is not red or green, we can use red or green to color this thing, because red and green is not anywhere in the neighborhood, and this is already colored 1, and then this is different from red or green, and therefore this will be valid coloring. because if I give red, but in case red or green came, suppose green came here, then give red to this, if red came here, then give green to that. So, it means that we can extend the coloring of V1 and V2 to the entire graph. In the previous case, when the code was there, you remember that the V1 and V2 were pre-colored. So, that means this and this has already got colors. So, therefore, we start, that is why we start from this side, because we have to extend that first and get colors of this thing and then extend the other side. So, I had forgotten to tell that. So, therefore, this is the way we prove that planar graphs are 5 choosable, and then it also, see, this also gives a different proof for the fact that planar graphs are 5 colorable, because the earlier proof used Euler formula and then the typical the Kempe chain argument we had used. So, you have used a somewhat different strategy of considering the paths formed by 2 different colors and some but in the last class we had done that, but here is a proof which does not involve any of those things, it is just an induction proof. But here the subtlety is in the induction hypothesis and the strengthening, the clever strengthening of the induction hypothesis, right. This is so with this we will finish this class, and in the next class we will consider the list coloring for edges. The edge list chromatic index we will consider the edge coloring version of the list chromatic number. Thank you.